I'm actually Venkatesh. I'm one of the organizers. It's Bob Meganson, and the other organizer is Wei Ho. We will meet later today or tomorrow. And I'd like to welcome you all here on behalf of the IAS. I appreciate everyone coming. It was a difficult travel day yesterday. And yeah, it was very nice to be part of the organizing of this workshop. I was saying to Juan earlier, usually when you invite people to speak at something, there's a hemming and hawing, and I have so many other things to do. And here, when we invited people, everyone was really eager, which I think speaks to the enthusiasm, the need for such a thing. Anyway, I just wanted to welcome you. I'm going to hand over to Bob, who's going to announce the speakers today.
Thank you. Anani Wachta, what do you say? Okay. I am of the Oglala Lakota Nation in South Dakota, and that is a warning. That is a welcome. Maybe it's a warning too. I don't know what. No. I promise that I will not need to attach any warnings to my introduction, because this is going to be a fabulous presentation. But I would like to begin by acknowledging that I am standing on the lands of the Lani Lenape people, who have been here for thousands of years and have learned to live in peace with each other. And it will be a wonderful day when the rest of us can learn to do that too. So with that, I would like to introduce Professor Karen Uhlenbeck, who I must say is one of our proud products of the University of Michigan, because I think your first academic thing that you did was to get a bachelor's degree from us.
That's correct.
And we have honored that later too, by also in 1984 or 86, we named you the UM Alumnus of the Year. And we've also awarded you an honorary doctorate.
In fact, they explained to me when I got this honorary degree that women, they weren't able to give women honorary degrees, so this was instead of an honorary degree. Not knowing that many years later I would get the honor.
We always get stories about how progressive we are, so now you've heard how it really is. Okay. But we are glad that we finally came around to realizing our error. I would mention, if I try to discuss all of the recognitions that she had, I would take up most of her time. I do have to mention the Abel Prize that she received. Even though there's no Nobel Prize in mathematics, that's often called the Nobel Prize in mathematics. And since you mentioned what has happened with women in the profession, it's been wonderful the way that you have paid attention to that. And for those who didn't know it, she gave half of that award that she received from the Abel Prize to organizations that are furthering the progress of women in research mathematics. So now I won't take any more of her time, and we'll turn it over to Professor Uhlenbeck.
Maybe it's a good introduction to my talk. In fact, I gave half my prize to organizations to promote minority mathematicians, which I felt was less appreciated in women, issues on women. And I also want to say that this is a talk about women, but I have my own interpretations on how you might listen to what happened to women when you're a minority, because they're not the same, but there's something to be learned from each. So anyway, I don't really know how to give this talk, because it's not, I don't give these talks very much. Some people in other fields just read their talks, but I don't think mathematicians can just listen. They have to actually look. I mean, it's and so I've written out what I'm reading, and so that gives you something to do. And then I'm going to do it to prove I'm a mathematician. I'm going to do a Blackboard part in the middle. Okay, the choices of careers for women when I was growing up were homemaker, teacher, nurse, librarian, waitress, and secretary. Actually, airline stewardesses were brand new, but they existed too. None of these appealed to me, but there seemed to be no prohibition against reading and learning. My mother was an artist who stopped teaching when she got married. Her main job was homemaker, although she painted on Thursdays and had many artistic friends, which were in fact mostly male, but some female. My extensive reading on science, especially physics and astronomy, led me to enter college as a physics major with no further goal in mind. My mother thought I could always teach, which I found uninspiring. The then USSR put up the first satellite in 1957, causing a shock to the West. A sudden realization that the United States was woefully behind the Soviets in science and technology led to programs encouraging students to study engineering, science, and mathematics to catch up with the Russians. These were in place when I started college in 1960. The need was so desperate that the rhetoric claimed, I mean, I vividly remember this, women and minorities are welcome, not out of any sense of fairness, but because we were needed. And I bought it. I started at the University of Michigan as a physics major, but fell in love with the mathematics taught in the honors calculus course. I switched to math when those people up there, started taking attendance in physics lectures. There were a number of other women students in my courses, and we were all encouraged and treated equally, despite the fact that there were no women professors and few job opportunities in our futures. The likely lack of professional opportunity for us women was undeniably bleak. I think it more surprising that our male professors encouraged us than that we women wanted to study math. We found the mathematics sufficiently entrancing so as to avoid thinking about the future. But what were my mentors thinking? I mean, most of them, I really would like to know what they thought of the situation. But very few of them were alive. So that's. I don't like presents, as I feel that they're given with expectations of return favors. But my memories of my discovery of mathematical ideas through courses and readings I equate with unwrapping the best presents I ever received. These were wonderful eureka moments, understanding what a derivative is, little boxes in the Uhlenbeck theorem. I think I have a very visual memory. Those boxes in that calculus class that, you drew them around things and located where the points went. This was the first invention of my own of a proof about normal families in a topology class, which I later found in the topology book, but it gave me a sense of real reward. The derivation of the Euler-Lagrange equations, and this talk is very much about Euler-Lagrange equations, so you'll meet them better. The simplicity, and this is the one that I find most amazing, the simplicity of complex analysis as opposed to the complexity of real analysis. And there was a lot more, but this is, since expectations for my future were dim, it all came for free. I didn't have any sense of owing anybody anything. And this is something that very few of us escape, actually. Life was not dull. Aside from taking or auditing basic graduate courses as an undergraduate, I spent my junior year in Michigan and spent 1 year in Munich and spent 1 year in New York at NYU in graduate school. Actually, the year in Munich was really interesting because, I had the style of teaching in my day at the University of Michigan was not one of professors coming in prepared to teach. They would come up to the board and they wander through it and, maybe you would get something at the end. Well, the lectures in Munich were beautifully polished. I mean, you know, they started, they were well prepared. I think they gave them year after year, but the contrast was amazing. So in 1965, I married my college boyfriend, who was a graduate student at Harvard in biophysics, and I transferred to Brandeis University to begin my studies in earnest. I had received an NSF graduate fellowship. I think they were relatively new and also kind of a result of Sputnik. So, you know, my career really rode on the tails of Sputnik. But I received an NSF graduate fellowship, but one of the wisest decisions of my career is I didn't even apply to Harvard or MIT, and I was accepted at the only place I applied, which was Brandeis. The second wave of feminism began during my undergraduate years, and the battle for women's equality was heating up. I had no interest in street fighting. I wanted to do mathematics. I didn't want to change the world. You know, it's so Brandeis was for me a wise choice. There was a minor amount of usual flack, which completely disappeared once I made progress in research. So I chose my thesis advisor and topic of study very carefully. Richard Pelley was an excellent lecturer. His lectures were enthusiastic, careful, and complete. He was always available, but I was even more drawn to the subject he was working on. So I remember distinctly thinking, do I want to work in this brand new field with new ideas and stuff, or do I want to prove something, some incidental special condition about boundary value problems for partial differential equations? And I didn't, there was no choice. I mean, okay. So I'm going to tell you about global analysis. I mean, it was, you know, there are all these waves of excitement, but of course, you know, 40, 50 years, 60 years later or something, people don't really recognize the excitement that went on when these developments occurred. And you know, to get into it as a beginning, as a relatively young graduate student was very exciting. It was global analysis was the hot topic of the day. I'm going to give you a try at setting the subject. I don't know whether you'll recognize a lot of the math, but I'll try to explain it. The study of differentiable manifolds from a topological viewpoint was flourishing. And rather than explain, I mean, so I'll say a little bit about manifolds later when I talk more about the details of the math. But for example, Steve Smale received the Fields Medal in 1966 for his proof of the Poincare conjecture for dimensions greater than 4. This theorem states that the smooth manifold of the homotopy type of the sphere is homeomorphic to the sphere. John Milner also received the Fields Medal at that time, in part for his study of the exotic differential structures on odd dimensional spheres. So it was, people were really discovering differentiable manifolds and discovering the basic ideas behind them, and it was a flourishing subject. Likewise, analysis to understand systems of partial differential equations, partly motivated by problems in physics, was in the process of development. Hormander's linear differential operators, it's Magnus opus, appeared in 1963, and his Fields Medal of 1962. I guess they already knew about it. It's in part due to the structure he created for the theory. So the subject of partial differential equations went from a study of special cases and working out details and even just trying to decide what kind of an equation it was, went from kind of fiddling around with special examples to an established subject where all the different function spaces that work were established. And so this was the formative years in some way as partial differential equations as we know it today. The subject of global analysis proposed to combine the two subjects. Okay, so it was a grand scheme of studying nonlinear systems of partial differential equations via infinite dimensional topological tools. So it was, okay, I'm going to say a little bit more about this later when I get to the math part of the talk. This is kind of the historical part. But in finite dimensional differential topology, the study is of finite dimensional manifolds in M and N and different manifolds that locally look like Euclidean space. That is, you can think of them as, you know all the examples of the toruses and spheres and so forth. And here's a little secret about trying to think about manifolds is that despite what everybody says, people really can't think about anything beyond three manifolds seriously. And there's another question, where do the examples of differential manifolds come from? Well, a lot of them come from places like algebraic geometry. A lot of them are kind of made up. You get this subject of differential topology, and then you invent, you see what you can do with it, and you play with it, right? But another source of differentiable manifolds is the solution space of a partial differential equation. And that has sort of kind of overtaken the field. If you actually look around at the research around, you'll find tremendous amount of work done on solution spaces, and which are often manifolds or almost manifolds or something like that. Okay, in finite dimensional so now in finite dimensional topology, the study of these finite dimensional manifolds. Points are the points in these manifolds, and that we can sort of imagine. We think of a torus and we think of a point in. But in the infinite dimensional global analysis, the points are functions, and these functions sit in some sort of space. And there are a lot of different models of what kind of functions, and if I wanted to go very complete, I could tell you, oh, it could always be a connection on a principal bundle and so forth. But basically, if you think about a match from one manifold to the other as sort of the elementary examples of spaces of functions, and remember that when we talk about the global analysis, or the points are actually functions, right? That's a lot of what I say in the talk won't make sense unless you make that jump from thinking of points as being sort of geometric points to the points actually being functions. And there are a wide variety of spaces to choose from. And basically, if you look at the subject of partial differential equations and all the applications, you'll see that every problem kind of needs its own delicate space. The whole subject goes around choosing the right spaces for the right problems and getting everything to match up. And as I said, I'll talk about this later. So now the year 1963. So this is the year, in fact, that I spent in Germany. And I didn't know anything about this till I started graduate school, but the year 1963 saw the publication of 3 promising papers that really drove the ideas of global analysis. I'll start with Morse theory, which is central to the work I did with Pele. Morse theory, so we have a function on a manifold, and we have critical points, which are minima or maxima, or places where the derivative vanishes in between. It vanishes. And so, so the derivative of the function vanishes at these points. And Morse theory connects the critical points of the function on manifold with the topology of the manifold. And in fact, the simplest example isn't even really that complicated. That is, if you have a function that goes to infinity and is bounded below, and it has 2 minima, it's got to have a saddle in between. We don't even have to talk about topology there. That's called the mountain pass theorem. But if you have a region in space of any dimension, and you have the function goes to infinity on the edges and is bounded below, it's got two minima, it's gotta have a salad. So, and then of course, it's very complicated to work all the details out, but that's the mountain pass theorem, and many people have reproved it in many settings without actually recognizing the simplest application is Morse theory. But, okay. It's still very striking the way Morse theory arose. Morse theory arose from looking for geodesics on a manifold. That is, if you're on in Euclidean space and you have 2 points, there's a unique straight line between them. But if you're on a manifold, like a sphere, then you actually have many different, you have many different straight lines, which are the shortest distance lines locally, not globally. So if you're on a sphere, if you have 2 points, the geodesic between gray arc between them is the minimum, but then it's got a lot of other solutions that aren't exactly minimum. And those are the critical points. But Morse theory was developed for this. And so later on, it actually became a foundational tool in the study of differential manifolds. But it came from infinite calculus of variations in infinite dimensional topology. So things don't progress the way you actually think they're going to do. Okay. Oh, yeah, I wanted to say one more thing about why global analysis. The Morse theory for geodesics is actually proved by approximating geodesics by short broken geodesics. That is, you have a curve and you dot a bunch of points, you take the shortest distance between all the little points, and you actually look then at the values of the points on the manifold as many copies of the manifold, and this is a function of them. And so the problem is, if you have a calculus variations problem that has more variables, how do you approximate it by a finite dimensional object? I mean, people really did try. You had a minimal surface and you wanted to approximate it by a finite dimensional problem. You can try to do it. Nobody, I mean, I don't want to say nobody's done it because mathematicians are very inventive, but they certainly didn't know to do this. Okay, so anyway, okay, I'm sorry. So actually, I also always want to mention, because this is really a foundational subject in what is really global analysis, Bott's 1959 proof of the Bott periodicity theorem using Morse theory of geodesics as a tool, and the beautiful of the calculus of variations enticed mathematicians to look at the subject further. So I'm sorry, I'm kind of lost in my, anyway, in Palais and Smale published a paper which circumvented the problem by looking at gradient descent curves on an infinite dimensional manifold. And so, and that way they were able to reprove the Morse theory for geodesics straight in the space of curves, rather than going to finite dimensional approximation. Another landmark paper in 1963, Ilse and Sampson published a proof that the energy interval of maps from a compact manifold into a manifold of negative curvature takes on a unique minimum. And this is a different subject, but it completely, people still talk about that paper because it's done not using gradient descent, which is would be an ordinary differential equations in infinite dimensions, but a heat equation, which is sort of like the gradient descent, but not exactly. And so they use that. And later on, I'll explain why you can't use the direct methods to find the minimum in a straightforward way. And I have to say, I was sitting in a course in a survey of, forget one of the courses, and Akshay and Professors Akshay and Lurie run a learning seminar. And one year they did nonlinear, Higgs bundles and things. And they quoted the proof of the existence of nonlinear heat solutions to the nonlinear heat equation that Eels and Sampson gave. So that's impressive that somebody's quoting your proof some 60, 50 years later. Anyways, so I'm going to have to. So. Last but not least, in 1963, the T and Singer published an announcement of their celebrated theorem, identified the index of a linear elliptic system on a manifold with a topological invariant computing from the symbol. And this was a very general theorem, and it generalized very important theorems like the Riemann-Roch theorem and the Hertzsprung signature. And some of the most important applications were in the future, if I get to them. That's my. Actually, it goes again. Bach's suite for unaccompanied cello. But you don't want to hear it twice. Okay, so the T-Singer index theorem, and my advisor had been at the Institute and had been asked to organize a seminar on this, and he organized a seminar at the Institute. He was very junior, and the notes from that seminar became a book, which was published the year I started working with him. And it was the first published proof in the paper, which is, so remember when you look at historically, if someone announces a theorem and someone else proves it, that still means the person that announces gets a credit. Okay. And so when I appeared on Dick's doorstep in the fall of 1965, he was giving a lecture course on the calculus of variations. And I was very enthusiastic about the lectures and even more enthusiastic about the global analysis. I have to say, Dick was not that enthusiastic about me when I appeared in his doors. You know, I walked in his door and said, you know, could I do a reading course with you? Or I don't remember what I said. And he sort of said, well, you know, I sort of think women should stay at home and raise children and so forth. And he doesn't quarrel with this recollection, by the way. and on the other hand, I simply ignored it. Because anyway, that's what everybody said at the time. And anyway, I also recognized immediately that if I were to fight this war, which isn't won now, right? I'd never get anywhere. I'd be fighting the war, which is something to do with your own safe, but if you want to do mathematics, that's what you want to do. So we started working together, and the subject never came up again. Okay, that was, it did once. He and Lippmann Bears had apparently a very interesting discussion comparing their women students. And Lippmann Bears is famous for having had a lot of women students. And Lippmann Bears said, well, the decision was that Lippmann Bears possibly Dick won on quality. So this was, I'm not really supposed to say that because I don't know how Lippmann Bears students would feel, but anyway, it's a nice story. Okay, so what was the research I did for my thesis? Okay, so I talked about this before. So we have functions, and again, there can be anything else, but think of them as maps. Let's think of the functions, and we need to make a function space of this. And we also have, we have variational problems, the style back in those days was interesting because everybody in their notes, you know, writes down to the integral of M, and then they write D, let's see, some L for Lagrangian, and D alpha F, F X, the X to the N. And, you know, they don't, this is the derivatives through or some order K, right, alpha less than or equal to K. So the style was very general, very complete. You started out with derivatives in any order and you prove things about it. And if you look at the textbooks from the time, which are impossible to read, they all start with it. So you have an interval like this, and F is a map from M to N. And you want to somehow make this into a function on an infinite dimensional space. But if you have to put some topology on the space. Now, so the good, when you build functions, the first thing you need to know, even if you're not in PDE, even if you're not in the subject, is you cannot use continuous functions when you're solving partial differential equations. It doesn't work. The inversions don't work. If you write down the inversion with a very simple Laplace operator, it does not map continuous functions to twice continuous functions. Okay. So you have to invent some new spaces, and the new spaces, the best new spaces are the Hilbert spaces HK, and there the norm of F is something like, and I'll use the same sum, alpha less than or equal to K integral over M of d alpha F squared dx to N. Okay, so this is the norm for them, and you say those are the best norms. And so let's go to the functional that we're actually going to want to look at, which is the integral of the derivative of the function squared. This is the most natural function. This is d mu. You're on a manifold, so you have to actually give it a norm, and you have to give it a measure and so forth. But the f of x squared d mu, and that's called the energy integral. And F is a map, as again, from a manifold to a manifold. And the critical points of this, if N is a real value, is reals, the critical points of this, and in this is case N equal R or S1, the critical points are solve Laplacian U equals 0. U is the minimum of the integral. And they solve Laplacian U equal to 0. And this is a very important subject. So you're kind of interested in what the Laplacian is of maps from M to the Laplacian is for functions maps from M to N. And you can use this. Mathematicians are great at taking an idea and generalizing it all over the place. So we're really taking the notion of harmonic functions, and we're generalizing them to maps between manifolds. However, so you actually look at it, and from the point of view of the calculus, you think, oh, I know what space I should use. I should use H1, which has the norm in H1. H1 is equal to the norm, the integral of the manifold of M d squared d mu plus the integral over M of F. Okay. So the only catch to that problem is it's a bad space for the infinite dimensional topology. That is, we try to look at maps H1 from M to N, and you can define it, but it's not a manifold. There's no way to go about it. So, this is the problem. We have a natural problem. We're thinking about it, and on the other hand, our natural problem doesn't. This is the harmonic maps of Niels and Sampson were the proof that there's a unique minimum of this, and the minimum is very smooth. I should say that when you work in one of these function spaces, one of the basic precepts of nonlinear partial differential equation is if you have a solution that's kind of wobbly and not very smooth, the theory tells you how to make it into a C infinity function. So that's a big step in the machine. So it's not a manifold. A manifold, except when the dimension of that, unless dimension equals 1. And that's the case with GED6. And we already knew how to do that. I mean, you know, the global analysis is not making much progress here. But on the other hand, so what was my thesis about? Well, my thesis was about really finding functionals that had some geometric properties that did satisfy the important conditions that you had to have Morse theory. And it turns out the integrals that I mostly was interested in is the integral of the derivative of f to the pth power d mu. And now P, this is the Sobolev embedding theorem. And in order to make a manifold of it, P has to be greater than the dimension of the base manifold M. The target manifold doesn't matter. That's somehow less important in the analysis. But this is, and there's a beautiful theory for this. And I worked out all sorts of stuff like that as an example of what was interesting. And but on the other hand, it's never really and I learned a lot of different machinery, and I've learned a lot of classical types of differential equations. In fact, the problem I spent the next 6 or 7 years on, when I was a graduate student afterwards, was to prove that critical points of this interval were actually smooth, not just wobbly functions that I found in this function space, but actually real functions. And it wasn't an important problem, but it grabbed me, and I learned an awful lot of mathematics by working on that problem, which I did solve 6 or 7 years later. And it was interesting because last year at the Institute, I heard it referred to in the first, that theorem referred to it the first time in an application. And I was really amazed. I also discovered that a Russian woman had proved it several years before me. On the other hand, the communications weren't great at that time. So, okay. So I got my degree and I went off to Berkeley. And for example, I was still, you know, I was more internally driven than doing, and my thesis advisor, well, you should learn general relativity. So I audited the year course on physics, basic physics. It was some quantum mechanics, it was some general relativity, and it was quantum field theory. But I never got to quantum field theory because Kent State happened in the middle. And all the classes were canceled, and there were I never learned quantum field, but I did learn differential geometry from my general relativity course. In any case, and so there's a lot to be said about the situation. The Vietnam War protests came at the same time as the civil rights movement. It came at the same time as women's liberation and action. Now, if I were to talk about this, we need another hour. So we'll just remember that this was a very interesting 2 years at Berkeley that I spent, and there was uproar all around me and so forth. And yet, somehow or other, it didn't influence the mathematics. I have no explanation for this. I mean, those years of my life were chaotic. I got divorced. I moved in with my boyfriend. I changed jobs 9 times, and I kept on doing math. I wish I could do that now. So,
can I ask a question?
Yeah.
Okay.
Sure.
So I was interested into this critical solution of the Euler-Lagrange. And when you say Morse theory, is it like index theory? Is it related to index?
Yes, it is. In fact, that lets me tell my story. Okay, so anyway, I actually, my research progressed quite a bit, and I got ideas from a lot of different places. I want to say I worked on Morse theory on Morse manifolds from taking general relativity, and I got interested in eigenvalues because I taught a course 3 times as an instructor, 1-year instructor at MIT on differential equations, and I got really interested in all those beautiful theorems about eigenfunctions of spheres and things. I mean, and I got interested, and I published quite a bit of paper. And looking back, I thought I was doing all right, but nobody else seemed to notice. but looking back, I was actually doing really well. I mean, so I was internally driven. I mean, there was no question about that given the whole situation. So, yeah, this is about the Morse index theorem. When you have a critical point. So now let's go to finite dimensions. Finite dimensions. You have a critical point. So I used E for energy. Let's use little e. E is a function from M to R. And in our case, this would be an infinite dimensional manifold, but in finite dimensions, it's easier to think about, right? And the critical point is df equals 0. And the Morse index, d of x equals 0, is a quadratic form. And the Morse index is the number of negative eigenvalues. So the Morse index of a minimum is 0. And a Morse index of maximum is the dimension of the critical point is the dimension of the manifold. But in the calculus of variations, we never have maximum. The function spaces are too big, and you can't have minimum. Well, you can have 2 level sets that go between them, but you don't get. Anyway, so that's an important part of the connection and the topology, because you find the critical points and their indices, and then you match it to it. It's a beautiful subject. And I learned it from Milner's Morse theory book, which I think is still a good reference. So anyway, so one of my stories about my research, the one I'm going to tell here is that you know, I was publishing a lot of papers, and I published a paper on the Morse index theorem for calculus variations problems. Okay, and it has to do with the fact that as you have a solution to the Euler-Lagrange equations, which are the equations for the critical point, and as you increase the domain, the index of the critical point increases with respect to the bounded value. Well, the paper I published was in a direct line. I referenced Birkhoff, Morse, Edwards, Smale, Simons, and myself. Now, I was doing the right things with the right people behind me, and but you know, nobody noticed. But I still got a tenure track job. So that was so. How did I get the Abel prize out of this? You know, I'm trying to look. Well, we'll go back to my thesis set. So if you look at this problem and you let the dimension of M be 2, okay, then you see for the dimension of N equals 2, E is almost 2. Not quite, but almost 2. And I've done a lot of estimates. And a postdoc at the University of Illinois in Champaign-Urbana came from Berkeley, having studied geometry. I was an analyst. And we started talking, and he told me about all the interesting problems you could prove about finding critical points Well, this is an energy. And the energy integral, so I was an analyst and doing all these general problems, and I didn't really know the geometric problems. But he was explaining to me how many interesting problems there were about finding, this is a manifold here, sorry, and dimension S2. Sorry, I'm clearly, this is S2. Okay. But F is now mapping S2 into any manifold. So you could actually find, so the question of finding critical points for this energy integral, and this was a very important problem. And I realized immediately that P was almost 2. So I simply took all the Morse theory you knew for P greater than 2, and we took the limit, and we discovered we rescued enough critical points to prove some important theorems. Just, so it was it's just as a side effect. And, this theorem is still quoted. When I get the Abel Prize, everybody talks about this theorem. So, I did a lot of things. And then, of course, something else magical happened, because I'm talking really about the revolution that occurred. And that is the physicists discovered the T-Singer index. Okay. They discovered the T-Singer index theorem is about a PDE on M. Okay, now how this PDE comes up is a lot of them come up in algebraic geometry. So, if M is an algebraic manifold, there are a lot of different classical partial differential equations, and the Riemann-Roch theorem for this is the surface is the fundamental one for this. Sorry. Oh, right. But the physicists were interested in something called the Yang-Mills fields. And they're interested in Yang-Mills fields. On R4. And I write this is actually S4 minus a point. And it's S4 minus a point. Maybe I should have said something about this over here. The energy integral in dimension 2 is scale invariant. And it doesn't see the scale. And so the important thing we did was that when we were trying to make something converge, it converged everywhere but over a finite number of points. And over those finite number of points, you could blow it up because the problem didn't see scale. And so that's how you find this. And the same thing happens here. This is not the time to get a lecture on Yang-Mills fields. This is kind of the historical lecture, but the Yang-Mills fields on R4 were very important. And they wrote down something called the self-dual Yang-Mills fields, which is, so I'll write down the word self-dual Yang-Mills. And the T-Singer index computed the dimension of the space of solutions. This was really, the physics community at once decided mathematics was worth it. So they spent a lot of time teaching the mathematicians about Yang-Mills theory, which is a very beautiful theory, but I was just completely, we could have invented it, but we didn't. And so the mathematicians learned everything from the physicists and got half the problems we work on today, it seems like to me, came from physics somehow. But so it was the beginning of this. But the Yang-Mills fields is, I'll write it down, is the integral. And in fact, the M4, it's a 4-dimensional of something called the minimizes, which is the energy of a connection. And it looks like this, But this one is scale and dimension, invariant in dimension 4, which is the important thing. And the thing was, I was just trained to do this problem. And so it fell in my lap, and I proved enough theorems that the physicists knew who I was. So this is a real accomplishment. So those are the papers that that's sort of what I say, how I got rich and famous. That was the code word we used. Now we're just about out of time, but I haven't had that much. Maybe the next part, the next page I'm going to miss because I was just going to tell you, and since for the last 40 years, I did a lot of research, and I like it, and I enjoy doing it, and a lot of my friends liked it, but it didn't make me. I was already rich and famous, but it never would have made me rich and famous. I wasn't in the right place in the right time, and never caught on. People don't quote those later theorems at all. I did it. And this, I'm with all the rest of the namely, most of the work we do, we love. Some of it's useful. Some of it, our friends love it, and we enjoy it, and it's rewarding, and it helps in our teaching, and maybe in the long run it contributes, but we don't do it to get rich and famous. We do it to do it anyway. So the talk is about the past. And so what about the present? Well, global analysis became geometric analysis. It was so called by S.T. Yao because he thought global analysis was too soft, too wobbly, no hard theorems in it. And here I don't agree with the dismissal of this change of attitude from seeing the partial differential equation as a specialized thing you computed with to seeing it as a grand scheme and analysis. And as a subject, it's still going strong. I mean, it was from a non-subject, it's become a central subject. And I have to say that it's not as exciting as it was in the beginning. So I don't necessarily think you should jump on the subject because it was exciting that long ago. Now, I want to say something about the diversity issues. A true revolution has taken place, not only in mathematics, but in current life in the developed countries. Women generations before mine really had little access to advanced education and professional jobs. There were outliers like Hypatia, Sonia Kovalevsky, Sophie Germain, and Emmy Noether. But an existence proof is very comforting, of course, but it mostly serves to emphasize the status quo is of essentially no women. When I gave a plenary talk at the International Congress of Mathematics in 1990, I was the second woman to give such a talk. Emmy Noether in 1932, almost 60 years earlier. However, immediately following me, there were many women speakers. And the last time around, the second woman got a Fields Medal. So it's changed. What made this possible? Did mathematics change? I don't think so. Maybe some people do. It changes. I thought how it changed. Did how we do mathematics change? Society around us changed. And when I was doing my mathematics and pretty much ignoring it, what was going on outside. And, important dates, of course, women getting the vote in 1920, 1964, that's the year I started graduate school, President Kennedy passed Title VII of the Civil Rights Act, which prohibits discrimination in employment on the basis of sex. And it was already, the Civil Rights Act already prohibited discrimination based on race, religion, and country of origin. What made a real difference in academia was the passage of Title IX in 1972. It was aimed at sports, but it prohibited discrimination on the basis of sex in institutions which received federal funding. Princeton immediately admitted women. The second wave of feminism perhaps began, to my eyes, in 1959 with the publication of The Second Sex by Simone de Beauvoir. But the important thing for me was 1963, The Feminine Mystique by Betty Friedan. It changed the life for all of us. I certainly read this, the Feminine Mystique, and it made me realize that I really didn't want to be a housewife. I mean, which was what I was supposed to be doing, in addition to my math, if I wanted to keep doing that. But anyway, and you need to credit the people outside math, like Gloria Steinem, Shirley Chisholm, and Ruth Bader Ginsburg, and the many other women. And in math, we owe a lot to the founders of AWM, Mary Gray, Lenore Bloom, Judy Reutemann, and then it goes on and on. Those were the first few. My mother went back to teaching after my youngest sister entered school. She had stopped teaching in 1936 when she got married, just because she got married. Anyway, so we have women doctors, women congressmen, and women professors. And we have, however, fewer women surgeons, fewer presidents, fewer partners in law firms, practically no symphony conductors. And then you can always pick up your favorite place where you don't really see anything but white males. And but of course, no human endeavor is perfect. Even each one of us can only do our best in any given situation. Anyway, I think I'll end here.
We do have time for questions because, as you notice, I think we may tell the speakers they've got 60 minutes, but we always allow them 70. Okay. Yeah, so there's another 10 minutes. That specifically is for this purpose. This conference is part of a series of conferences that's sponsored by the Mathematical Sciences Institute Diversity Initiative, of which IAS is one of the, I believe, founding members. So the goal of these things is for you as, primarily, but not exclusively, but primarily early career mathematicians, somewhere in the very early stages of your career, to hear, first of all, mathematics. If you have questions about the mathematics you heard, I encourage you to ask them, but also about how this profession works from people who have been there. So please take advantage of that. And with that, I will turn it over to you and to Professor Uhlenbeck for questions.
Oh, you got good. I know who I want in the front row of my lectures.
All right, so I had a question. For the Uhlenbeck equation.
Yeah.
I've seen work where people have the second order ODE.
Yeah.
And then they derive a first order ODE.
Ah.
And then they look at the geometry of the manifolds that comes out of this first order ODE. As far as manifolds, I mean, like if you have a fixed point in the manifold, like a fixed point in the ODE, like it can be attracted and you get the unstable, stable manifold. So what they do here is the critical solution of the Lagrange equation in this second order, in this first order ODE is actually what they do is like when you look at the second order ODE, it's like a second variation, right? So what they do is they linearize the critical solution.
That's the second variation.
They linearize the critical solution, and then to compute, they use the index theory to find where you have like what you call critical points.
Yeah, the index. Yeah.
Yeah, the index, and they relate the critical points to the number of unstable eigenvalues.
Yeah.
And so they could actually then notice whether a solution is unstable or stable, but they relate that to the relative local minimum, right? And then they compute the functional to find the global minimum over a certain bounded domain. Right? So I don't know if I'm making sense. So my question is does it depend on the how you define your Lagrange? right? Do you always get smoothness in the solution of the critical solution?
Well, I honestly thought you did until I found one recently that I can't prove boundedness is the derivative. And I didn't know such a thing existed in 2 dimensions. So the answer is that I know a problem where you can't. So, but that was actually a big part of PDE when I was growing up, so to speak, is finding solutions and then proving that they were actually smooth solutions, not just in a function space somewhere.
Other questions? Yeah.
What's the intuition for calling it an energy integral?
That surely comes from physics. I mean, the thing is that, sure. I mean, okay, I think the simplest explanation for that is from classical mechanics, right? Where you have, and this comes from classical mechanics classical mechanics is about ODE. Is ODE, right? And the theorem is that the motion comes from the kinetic energy. I mean, the energy actually it's the action interval comes from minus potential energy. Okay. Now the kinetic energy is really we're now just in function space, so I'll call it x instead of f. It's really x of t squared. I think there's a half. There's a mass here too, and then there's whatever. This is the standard one, so it's the derivative squared. Now, as the subject developed, people are interested in the Laplacian, which is also a fundamental subject. And the Laplacian is just, and then again, I think it's the same origin. The energy integral of f for the Laplacian, f is now a map from actually, classically, it's a domain in Euclidean space to R. And you take the dx to the n 1/2. And so this is the Laplacian is a very basic thing, and the energy integral is what you use, and you compute the Euler-Lagrange equation, so you get Laplacian of that. In fact, you can define the Laplacian best. In fact, if you want to change coordinates in Laplacian in Euclidean space, you do it by writing down the action integral and changing the coordinates in the action integral. I mean, and the energy integral, a lot easier. So anyway.
So I have a career question if nobody else has a quick question. As I mentioned, one of the things that we like to do is to hear from people who have been there about different things involving this profession that you decided to get involved with. You mentioned Lenore Blum. Lenore has had a huge impact on my own career, and it's not exactly mathematical, but it's in telling me how to keep going when something wasn't working.
Yeah.
That I felt. Did you ever have experiences like that? And I wondered what you told.
Well, Lenore Blum and I were together at Berkeley during those critical years, and Lenore took to the street fighting.
Right.
So she got a job in Mills College and changed the math curriculum and got involved. I mean, changing the you have no idea what a sexist organization the AMS was. I mean, you know, that's and I mean, these old guys had to be booted out. And people like Lenore, were instrumental in doing that. And then mid-career, then after a while, she thought maybe she'd go back to math. And there was a special program from the NSF about just allowing women to reboot their careers. And she actually did a postdoc. I'm not sure, I forget who it was with. I know who she ended up working with, maybe Mike Shube even. And she did, and she learned computer science. And she's now, she became a professor at Carnegie Mellon and is really very, in fact, most of the women from those early days actually succeeded not only well, but spectacularly well. I think that's because we knew what we were up against. We had no illusions that it was easy.
In fact, there's this award, the U.S. Presidential Award for Excellence in Science, Mathematics, and Engineering mentoring. It's awarded, it's a White House award given by the president that's awarded to very few people each year, and she has received one of them.
Yeah.
Anyway, other questions? Yes.
Looking back, on your career and your path to where you are now, is there anything that you wish you had done differently?
But that comes later. I'll tell you what, I had not realized that one of the jobs of someone in mathematics was actually to proselytize. That is to actually decide what your problems you thought were important and put them out there, giving the status quo a real kick in the pants, because the status quo actually hangs around for many years. And I wish I had simply proselytized for stuff that wasn't standard. I mean, I would get up and give my talk on integral systems, but I didn't proselytize enough about why this was interesting to do. And that's what I really wish I'd done that. So.
Other questions? Yes.
So I'm wondering, are there any topics that nowadays you feel like are sort of in that blooming stage, the way of global analysis was back then?
I'm actually really a little bit out of it. I mean, I got involved in a really new topic, which is completely different, but it is sort of an offshoot of the calculus variations, and it has to do with Thurston theory and best Lipschitz maps and so forth, but which I find very exciting because no one did anything. It's really nice to do that. And somebody is interested in it more or less. But I don't know, I was interested in AI for a while because I thought this is a problem. This is a really interesting subject about calculus of variations. It's not the calculus of variations, it's actually the finite dimensional problem of minimizing something, but in a very large space. And if you took the calculus of variations and you didn't know the geometry, you would just approximate it by a whole bunch of points on the computer, and you would have no idea what happened. If you had, you would have, it's knowing the geometry, knowing the Euler-Lagrange equation. So I have the feeling that these minimization problems they're doing them in very large spaces, and they work beautifully. Steepest descent is the greatest subject, but they don't really know what's happening. I mean, the geometries. And I have talked, it really is in the formulation of the data and the geometry that a lot of the key ideas are. On the other hand, it's a very crowded field. And, if I were to go into it, I would find myself a mentor. I would not go into it on my own because it's such a hot topic. But it is very interesting for somebody who's worked in calculus variations. What are these people doing? What is the geometry they're missing?
Well, Professor Uhlenbeck has done a wonderful job of setting us up for a great conference. So I'd like for us to thank her again.